Good afternoon. Welcome. Thank you for being here.
Hello,
We'll
Colin.
just give it.
Again. Hello, Paul.
We'll give a couple minutes to let people join, but we'll start nicely on time.
Mm-hmm.
Hello, everybody. Good afternoon from Spain. Good morning to those of you in the US, and afternoon as well for the ones in Europe. Thanks for joining this second session of today's webinar on 3D laser Doppler vibrometry with a single Ommatidia Q2 head, laser Doppler vibrometer. My name is Oscar. I'm starting slowly to give people a chance to join, but thank you for being on time. Get going. For those of you who don't know me, I am a product engineer here at Ommatidia LiDAR. I joined the company 1 year ago. My background is mechanical engineering, and I did my PhD in applied physics, fluid mechanics. I spent 10 years doing research and lecturing in fluid mechanics. And eventually I left academia to discover other paths. And now I take care of product demos to potential customers, support to existing users, and developing applications and workflows for our technology. And this is something that I really, really enjoy. It's one of my favorite parts of the job, working closely with academics, engineers in industry, and coming up with nice ways to exploit our technology and do nice science and engineering. I guess most of you are already familiar with our technology, but let's just start by doing a brief overview of why our approach to laser Doppler vibrometry and metrology is different from other implementations. As you know, laser Doppler vibrometry is measured is based on interferometry, right? In our case, instead of having classical interferometry components inside our devices, we have a photonic integrated circuit. This is a circuit printed on a silicon wafer that instead of having electron guides, it has photon guides, wave guides. And in this chip, we have 128 interferometers that allow us for super dense measurements and simultaneous measuring points. In the Q2, the one which is the latest generation of our technology, we have 65 laser beams that measure simultaneously, but we have 128 interferometers packed into the chip, which allows us for a more steady, a more robust reconstruction of the data, and therefore we can eliminate speckle noise. We can reduce speckle noise to a great extent. And as you know, this is one of the problems. Speckle noise is one of the ghosts that hunt laser Doppler vibrometry. Right? Our devices can measure at up to 50 meters, and they can be extended under certain circumstances. They're very good at super low frequency, down to DC. The lasers are eye safe and infrared with low power. They're quite easy to use. They're straightforward to set up. There's no need for pre-meshing or pre-definition of the points that will be measured. And the device is contained in this box that you see here. There are no additional electronics or racks, so this is very portable and deployable in the field. One of the most important characteristics of our devices is their dual functionality. And this is the heart that allows the technique or the workflow that we are going to show today, that we can do distance measurement and velocity measurement. So we can do high quality metrology. This is like LiDAR, but instead of being a time of flight LiDAR, it's a continuous wave, a frequency modulated continuous wave LiDAR. And this allows for precise metrology. And through Doppler effect, we measure velocity like in laser Doppler velocimeters or vibrometers. And by using these two functionalities is that we will be able to extract 3D vibration measurements, or rather reconstruct 3D vibration measurements only using one hand. Okay. Before we go onto the workflow, that is the main subject of today, I want to share with you another recent development that is fresh out of the oven in a beta version and will very soon be available for our existing users. Here's me winking at you, Todd. We have implemented the Pyoma Python library into our data processing software. Right, so now we can perform operational modal analysis within our software interfaces, and new functionalities will be coming up, will keep coming up and being added. And this is, again, a very exciting development for us that, well, this responds to requests from users. So you'll be hearing more about this for sure. And if you want to approach us and talk about this, we are always glad to discuss and have meaningful interactions. With this, let's go to the matter of today's meeting. This is another development that we've been working intensely now during this year, especially the past couple months. And this is a workflow for 3D laser Doppler vibrometry using a single head, right? So this is based, like I said, on the fact that we can do both metrology and vibrometry. This is the setup that we've been using for tests. Very important part of this setup are markers that will be found through metrology and will provide the different reference systems to be combined into a universal reference system with which we will reconstruct the 3D views. We are, of course, leveraging the fact that we have 65 simultaneous beams that allow us for a dense parallel acquisition, and also allow us to capture transient phenomena along a line while we're measuring. We are also using some other features of the device, such as the digital output channel that we have, which will help us trigger an automated hammer in this case. We also have in the Q2 an analog output channel that allows us to send signals such as continuous sine waves or frequency sweeps or noise that can also provide means of excitations for shakers or speakers, for example. We're not using that in these tests, but we have an analog input channel through which we can connect an accelerometer, an instrumented modal hammer if it has a 4-cell and we want to do FRFs, or a tachometer if we are dealing with a rotating machinery, for example. And the other feature of the Q2 that we are indeed using and leveraging in these tests is the speed sync, which is an additional external single laser head that points at a fixed position. Actually, the position at which the speed sync is aiming is marked by this sticker here. And this is measuring at the same point all through the workflow, and this will allow us to do phase synchronization, phase alignment, right? So what we will do here through this workflow is we will acquire multiple line of sight vibrometry views of the same structure, and we will keep metrology measurements attached to every vibrometry sample. This will allow us to reconstruct the physically interpretable 3D modal velocity field, and we keep visible quality checks at each step of the workflow. Why do a 3D reconstruction? Well, because after all, laser Doppler vibrometry is fundamentally a line of sight measurement technique. Right? And this is already valuable, very valuable, but it means that every point that we measure with an LDV is giving us the velocity component projected along the beam direction, right? So for many structures, especially curved or asymmetric parts, this is not really enough to understand the real motion, right? The surface can be moving tangentially and out of plane, a combination of these, and one view alone cannot really separate these components. Then the 3D workflow is our way of using the metrology and multiple viewpoints to recover a vector velocity field, not just a scalar line of sight map, right? So let's go through the workflow. I will show you the different steps, the different motions, illustrating the control software and the processing software. If at any point you have questions, please raise your hand. We'll allow you to open your microphone and we can discuss. And otherwise, at the end, we will also have some time for discussion. Okay, the workflow in a nutshell is, well, we'll use at least 3 different views, like in this case. We will acquire geometry by using a metrology measuring mode and velocity for each one of those views. Then we will have to pre-process and condition the data to get it ready for the 3D reconstruction. Then we'll start the 3D reconstruction by registering the different views with their targets. And finally, we will go to the reconstruction and export of the 3D vectors, right? And once again, we're leveraging the fact that we have a speed sync external head, that we have digital output and the analog output and input channels that allow to synchronize experiments and instruments in multiple settings. Okay, so let's start with the data acquisition. This is a screenshot of the software that we use for controlling the Q2. The Q2 has its own onboard computer, and this is operated through an external computer that connects via remote desktop. It can connect remotely, like sometimes I'm at home doing tests with the device that's here in the office. And everything is controlled inside the device itself. Right? Like I said, setting this up is very straightforward. No need for pre-meshing or pre-programming the point. Once we have this RGB camera that allows us to see the device under test, have a virtual projection of the 65 infrared laser beams that we have for measuring. And defining a scan is as simple as going to this current angle box, putting an angle value, pressing enter, and then the device will rotate counterclockwise for negative angles, clockwise for positive angles. And we need to find a good start angle and a good stop angle that cover all the field of view that we want to scan, right? Once we have the start and the stop angle, we have to define the step, and this is how much the device will move in each step, right? You will hear me sometimes saying frames. We call frame every stop of the device, every position that it measures on. And whenever I say channel, I mean each one of the 65 laser beams. Right? So we're measuring with the 65 channels, with the 65 beams simultaneously on a frame for as long as we establish in the time per step box. And once that frame is done, the device will rotate by the step amount and measure again, right? And in this case, we also have the instrumented hammer that will be triggered by the digital output every time the device is ready to start capturing a new frame. Right? But okay, step by step, going in the data acquisition, we first need to accurately find and register the markers using the intensity imaging and metrology. And let me go back and tell you one more feature about the Q2, this oversampling parameter here. This makes the laser beams move up or down, up and down, actually. And if we set an oversampling parameter of 1, this means that we will take one measurement along the line. If we do oversampling 2, we will take one measurement. I don't know if you're watching my head, but we will take a measurement here, then move the lasers down a bit and take another measurement along the same line, but in a slightly different position. So the oversampling corresponds to spatial oversampling that allows us to take measurements with a very, very high spatial resolution. And that's exactly what we're leveraging for finding the centers of the spheres of these markers precisely, right? These are polished steel spheres. They're very specular surfaces. If you see this intensity image here, there's very little signal all over the place, except for the center, the very spot where the laser hits precisely at the center. There we have a very high intensity value, and this is what allows us to then perform a metrology to measure the exact distance to this point, right? So first we check for intensity. It's just sending the signal, seeing what is the intensity of the signal that is coming back, finding the point with the highest intensity, and then performing a metrology measurement exactly on that point. And we'll do that for the 3 spheres. We will register them, and this will give us the coordinates from the point of view of the device at this position, right? And this is what we will later combine for a single unified reference system. Once we have the position of the spheres, of the markers, we perform metrology and vibrometry scans on the device under test, on the object that we are measuring. Right, so this is, here you see an example of a point cloud from one of the views, right? And the metrology and the vibrometry scans will be performed on the exact same points. So all the points that you see here on the point clouds are the points where later on we are going to scan with the vibrometry measurement. And the vibrometry measurement, I already explained what it consists of. The device is positioned for measuring. We trigger the hammer, it hits, we acquire data for, I think in this case it was 5 seconds. We let it measure for 5 seconds, we rotate it, trigger another hammer impact, and repeat until the end of the scan. And all through, this guy is the speed sync. He is measuring at the same point, and this will allow us to align the phase. Because of course, the 65 points that are measuring simultaneously are in phase, but when we move from one frame to another, we are not necessarily in phase with respect to the hit, and we use the speed sync for this. Right, this is important. The hammer, the automated hammer that we're doing, does not have a force cell, so we are not doing force normalized FRFs. Right, the speed sync is only here for aligning the phase between impact responses, so that we can reconstruct one selected response component. Right, this is actually what the workflow will give us. We'll do reconstructions at a selected frequency component, not a full reconstruction of everything that's going on in the vibration. Okay, so that's the workflow for data acquisition. And this finishes when we have the following data assets for each view, right? We take the intensity measurement of the device. This is a good practice. This is one of best practices for using our devices. Make sure that the device is reflecting enough signal back into the Q2, right, such that we can have high quality measurements both in metrology and vibrometry. We then take the metrology view, the vibrometry scan. This is the full vibrometry scan. Well, these are 65 channels acquiring at 40 kilohertz each. So data accumulates easily if one performs long scans. But then in the pre-processing, in the later stage that we will discuss, one can decimate or downsample the data to an appropriate acquisition rate, which suffices for the spectrum that we are interested in. This makes the data somewhat more manageable. And we have the artifact of the spheres that we registered in the first step and exported as a CSV. Right, so we have all these for each view. As you see here are the assets or the artifacts for view 1, and we will have that for at least 3 views or more if we want to reconstruct a broader field of view. Right? Then we go to data preprocessing. Okay, data preprocessing is done in another instance of our own software, right? In the beginning, those of you who have our devices since a few years, in the beginning, everything was done in all the processing of the data was done in Python notebooks. This we released in January this year. We finished developing the first version of this. This puts all the knowledge that we have acquired on data processing into a nice graphic user interface that is quite intuitive and simple to use. And this allows us to visualize and process data. And as you see, we keep adding tabs with more functionality, right? So the data preprocessing that we will need for this case is verifying the velocity demodulation, right? One detail here, for those of you who don't know, our data are exported in HDF5 files. This is an open format, hierarchical data format. This is very good for high performance computing. This can be opened in MATLAB, in Python, in different software. We can also export data in the format in universal file format for Siemens test lab. So those people in industry using Siemens test labs can also process our data using that. And if you're not afraid to program, this can be inspected in Python, and you can program your own processing routines. Right. So we verify the velocity demodulation as the first step. The H5 already contains demodulated velocity according to parameters that we set up in the Atelier software. But in case that demodulation was not completely satisfactory, we can reprocess and demodulate the data here. We verify then the spectra and the peaks. The spectrum and the peaks should be the same for the device. If the experiment is the same, the viewpoint doesn't matter. We should recover the same spectrum. And we see that this is the case in practice. And like I said before, whenever it's possible, we downsample the velocity to keep the size of the files more manageable. Right. This is one of the other tabs of the processing software where we can see the line of sight maps for the different modes that we identify in the spectrum. Where's the spectrum? Here's the spectrum. So we identify the spectrum here, the peaks, and then we go to mode maps, and this is where we can see what mode shapes we have at each peak frequency. All right, so once we've done the data pre-processing, we can go on to register the data assets towards the 3D reconstruction, right? So the software, everything here is organized around a project file, right? Where each view, like we said, has its own artifacts, metrology, intensity, and vibrometry, and perhaps additional support data, right? And there's a practical point that is convenient to mention, which is portability. The project format is stored in a JSON file. This can rely on relative paths, or it can be based on environmental variables. And all the process settings and the quality control summaries are saved with the project and with the exported result. I mentioned this is important because it matters for support, right? If a customer, if a user sends us a project with its export summary, we can see what was actually run, and we can provide remote support quickly. Right? Okay, so we start with the marker registration, right? This is the first major step, is putting all the views together in a common coordinate system, right? Like we said, the workflow uses spherical markers at the registration reference, and this is deliberate because we want a controlled and inspectable registration target rather than just trying to stitch matching point clouds and hope that the surface is distinctive enough so that we will be able to recognize some points and use them to stitch the point clouds together, right? This is a lot more reliable. And like I said, this leverages the fact that our metrology is very precise, and we can find the center of the spheres with a high precision, with a micron precision. And yeah, so using markers is a lot more reliable than stitching point clouds of an object, right? So we load in the software for performing the reconstruction. We define how many views we have. We load the artifacts per view, the metrology, the intensity, and the metrology, and we load the marker CSV files. Right. Once, so the first step is registering the 3D point cloud and merging it. I'm showing you an example here where we have the markers from the three views. In this case, I am not terribly happy with the one with the reconstruction here. It has like 5 millimeters offset. There's probably something I didn't do correctly at during this test. But we are, right now this is at a stage where this is semi-automated, and the finding of the markers is very straightforward and very quick. And well, once with this registration, we have the view of the 3-point clouds set together. We see the regions where there is overlap between the 3-point clouds, regions where only 2 of them are together. And of course, if we want to do a full 360-degree reconstruction, we will need to use some more views around the object. Right. So once the 3D point cloud is registered and merged, we can go to run and export the 3D reconstruction, right? And here there are a lot of different options, and the software is already prepared to deal with quite a few of them. And we will, of course, keep adding more as they come up from the feedback of our users, right? In this case, it's very important to establish that the acquisition mode is impact response, and it will require phase synchronization with the speed sync, right? This is a very different processing than if we had a continuous sine wave providing the excitation. Right? We need to define the frequency at which we want to do the reconstruction. Like I said, this is going to be a reconstruction at a fixed frequency, which can be or not a modal frequency of the device. And then we have different setup parameters as interpolation strategy, maximum interpolation distance. Why is this important or necessary? Each view is performing the vibrometry on the same points as the metrology, but the different views are not falling exactly on the same points, right? So according to the settings of the step and the distance that we had to the device, we have to establish a maximum distance through which this can look for neighboring points and interpolate, right? We need strict, yes, something that's very strict. Minimum views have to be 3 if we want to have a proper 3D reconstruction. We can have more than 3. If we have less than 3, we can provide nice visualizations, but this is not really a 3D reconstruction. Right, and well, there's a lot behind this, of course. One needs to play around with a parameter, experiment carefully. Like I said, there are quality checks embedded and shown with each step, such that we can keep track of the sense and meaningfulness of the reconstruction that we're making. Once again, our code is all based in Python, and it's fully inspectable for quality control. I mean, I worked as an academic for several years, and many of you are as well. In academia, we don't like black boxes, so this is all transparent so that we know, you know, what is being done at each step. But it's also packaged into a user interface such that if your expertise on filtering and data processing is not that's not your field of expertise, you can still operate that with the guidance of the user manual and perform successful analysis. And once we've ran and exported the 3D reconstruction, the results are exported as VTKs. These are visualized, so this can be open in ParaView or other commercial and free software. And there's a lot of different options for visualization within this interface. Other things that we are developing that we've been working on along this are tools for validating the workflow and the measurements using synthetic data, and also to help us plan the views. I mean, it's important where we position the device in order to maximize coverage and overlap of the field of view, but we also want the viewpoints to be different enough so that we can properly reconstruct the 3D vectors. Right, and the next step that is being developed very carefully is using this for strain calculation. Right, this requires very high quality measurements, because then we need to perform the spatial gradient of the velocity fields in order to be able to calculate strain. This is something that we are working on, and this is very exciting as well. This will be available soon as well. And to wrap up, I'd like to point out the advantages, the practical advantages of this workflow. Right? We have 65 simultaneous beams that measure many points in one acquisition. This captures transient effects, and it also eliminates the need of pre-programming the scanning points. This is compact. We perform this with only one sensor head. This is easily deployable in the field. There's no big racks of electronics. The workflow is simple, even though this is an advanced technique that is using top front technology. The workflow is simple in itself. It's straightforward to learn how to do this, even if it's a very advanced experiment. The workflow is completely open. The data are open format. They're inspectable. The algorithms are also adjustable. Like I said, this can be exported as VTK or CSV, and also for a Siemens test lab for those who use it. LiDAR and LDV, this can be used for pure metrology. I mean, we can use this for metrology and laser Doppler vibrometry, which is a unique characteristic of our devices. And also the fact that we are a small company with former academics and people who know the requirements both of industry and research. We are very responsive for adapting workflows and developing tools that meet customer needs. We are very happy when users get to do interesting science and engineering using our technology. With this, I've gone through what I wanted to tell you today. There's time for questions, discussion, and yeah, please raise your hand if you want to ask or comment something. Let me allow your microphone. There, if you open your microphone, we will now be able to hear you.
Hey, great. Can you hear me, Oscar?
We can hear you loud and clear. And if you want to put your camera, we can also see you, because I don't think we've seen each other's face yet.
Hey, hi. Yeah,
Hi, Todd.
Oscar, thank you for the presentation. And let me say just congrats to you guys on all the advancements in your hardware and software. It's nice to see. So I have a question about the 3D measurement capability. So, of course, having 3 or more views allows you to to do measurements on an entire 3D structure and to go all the way around and measure points on the front and back and so forth. Are you, if you only measured a single point of view, just with one position, can you get a 3D measurement from a single field of view, or do you require multiple camera or multiple device positions?
You require multiple positions to be able to reconstruct. I mean, if you are measuring a completely flat surface and you know the normal vector to the surface, you can do like the projection of the line of sight velocity vector onto the normal, but that's about it. You cannot reconstruct the full 3D vector out of just one line of sight view.
Okay. So in a typical 3D LDV setup, you're going to have 3 cameras simultaneously, and you set the measurement up so that all 3 devices are pointing to the same location on the structure. So when you're moving the unit from one position to another, how do you ensure you're pointing to the same location? Is that through the use of the three targets, the fixed
Exactly.
targets?
Yes, that's the crucial part of it. The device, the Q2, the vibrometer can move, but it's crucial that the markers stay at the exact same point. Well, the markers and the object that you are measuring. This is the key for everything.
Okay, great. Thanks for that. That was clear.
Oh, thank you for being here, and thank for your question. We have another question from Keshav. Let me allow your microphone. Now you can unmute yourself and we'll be able to hear you, Keshav.
Hi, Oscar. Yeah, thank you for the nice presentation.
Thank you.
Yeah, I have a question about do you also evaluate the uncertainty? Because I see the markers are kind of large, like that you are, the markers that you are using to provide the reference for the different field of view from different positions, they are kind of large. So do you have the uncertainty in measurements, like for the velocity, while you are viewing from different positions? Do you evaluate the uncertainty, or do you know what will be the uncertainty of these measurements?
The uncertainty, you say?
Yes.
No, can you clarify your question?
Okay. So my question is
okay.
like
Yeah,
when
you say that they're large, but we're only seeing one point, right?
Yeah, so they are large, like those markers are large, and then I think there will be some uncertainty in spatial resolution that you're seeing, and how does it affect the measurement uncertainty?
Okay. Yes. Well, actually, since our devices can do both metrology and vibrometry, and actually the company started doing metrology. This is something that we work a lot on in other projects that are purely based in metrology. And this kind of markers are standard and common in high precision metrology. But there are different ways to approach the markers. In this case, like I was saying, these are polished spheres, right? And polished spheres are very specular, which means that when the light comes into them, it bounces off with the exact same angle, right? And if you noticed in the intensity images that I showed, we see one point of the sphere, right? Because it really gives signal just at the point where the light is hitting perpendicularly to it, right? And we reduce the uncertainty of that point by using, this is something that I did not mention. Well, I did mention the oversampling, right? The fact that we can move the lasers up and down. So those intensity images you saw were taken with an oversampling factor of 40. So the lasers were, the LDV was positioned at such a distance that the distance between two laser beams was perhaps 1.5 centimeters, and we took 40 points in between that. And if we're not sure, we can even take 80 points in between that. So the displacement of the lasers when searching for the point is very, very small, and we can find it with great precision. Actually, for the last measurements that I was doing, I was finding the centers of the spheres with a standard deviation of 10 to 15 microns. So it's quite precise. There are, however, I mentioned the metrology because there are other approaches in which spheres are used that are completely white, and they give a lot of signal, and then you have a lot of points on the sphere, and you can search and fit the radius. This is another approach for doing it. And this is, to a large extent, a matter of preference of the user and of the situation that you're measuring. But yes, in a nutshell, to resume, the fact that we can move the lasers very accurately allows us to determine the center of the spheres with confidence and precision.
Okay, yeah, thanks. And I have another question. So actually for 3D LDV, so you are collecting data at 3 different time periods, which are not synchronous to each other, and then actually you are synchronizing all them together to evaluate the 3D velocity field. So how, I mean, given that, like there can be some differences in the vibration of the object that we are measuring for 3 different like measurement periods or for 3 different sampling times. So how do you accommodate that, or how is all it done?
Yes. Well, a key part of it is the speed sync, right? And the fact that it's measuring every hit that we're measuring, the speed sync is measuring at the same point, right? And also, you need good instrumentation. You need a good reproducibility of the impact force from the hammer. But of course, there is variability, right? So the speed sync allows us. It also has the speed sync has a much larger sampling rate, so it allows us to align the phase, and that's what we do now. We just align the phase using the speed sync. But we can also, and this is in the next implementation stage, we can also normalize the amplitude of the velocity. And that helps us correct for variability in the impact force. And then, well, there's just part of the uncertainty and variability that one has to learn to live with. But of course, if you have an instrumented hammer with a force cell, that further reduces the uncertainty and allows you for nice normalization and going into FRF type of calculations.
Okay, thank you. Yeah.
Yep. Thanks a lot, Keshav. Anything else from your side?
No, I'm good. Thank you.
Okay, thanks. So let's go to Othman, who has had his hand raised for quite a while. Now you can unmute yourself and we'll be able to hear you, Othman.
Hey, Oscar. Thank you for the presentation.
Hi, Othman.
Oh,
well,
good to see
thank
you.
you for coming to the presentation.
You're welcome. You're welcome. Yeah, this is very interesting and very exciting. Like now, being able to do 3D measurements with one head. I just have a question. Maybe this is something you mentioned. So when you measure the same test from different angles, so do you create a surface out of the 3 data points and then interpolate the velocity field and then reconstruct the 3D field? Or how do you do it, knowing that the points you sample for each angle are not necessarily on top of each other?
Yes, exactly. So we have the 3 different views, right, with their markers. Each has its own reference system where the Q2 is the origin. When we combine them, we bring them into a unified coordinate system, right? And we bring the 3D point clouds, the 3 3D point clouds into that system. And then, yes, we have to interpolate. I mean, there's no other way around that. And one of the parameters that we have when tuning the settings for the registration for the 3D reconstruction rather than the registration is the interpolation distance, right? And we have to define that sensibly according to the step. That the distance of the Q2, the step. I mean, in the end, the distance of the Q2 and the step will determine the distance between two laser beams, right? And you have to set. This is again, part of the trade-offs, right? The finer step that you will have the points closer to each other. The setup and the scan will take a longer time, but you will have to look. You'll have to look in a shorter distance for the nearest neighbor, right? But yeah, there is no way around it. You have to interpolate in order to bring the vibrometry from the different viewpoints into coincide.
Nice, like using triangles between the closest three points or 4 points. Like, let's say if you have a point in the middle of other points, like do you use triangulation or how do you interpolate? I mean, this is like a kind of a technical question.
Yeah, this is like, it has several interpolation techniques. The one that seems to work best for me in the experiments that we've been using is the nearest known neighbor. And you define one of the parameters is the number of neighbors that you allow it to consider, right? You can make it very stringent and say 4 neighbors, or you can let it go up to 8 or 10 neighbors if you're really loose. And I mean, that will smooth things out and smear them.
Yeah.
But it depends on what the spatial resolution of your scans was.
Okay. And here in this case, do you also take into account the angle of the beam between the laser head and the point? Because, for example, for a spherical surface, the angle changes, right? Even if you are at a medium distance. So do you take that angle into account for each point?
You mean like the line of sight angle, the angle with which the laser beam is impacting? Yes, you take, and that's all known, right? I mean, you know the angles of the laser beams, you know the position of the device because it has the IMU, so you know the exact pitch, roll, and yaw of the instrument, you know the angle, and you know the point. So yes, that is accounted for.
Okay, great. And maybe one final question, just for those references, for those spherical references. So what's the minimum number of those references do you need for these 3D measurements?
The markers, you mean?
The markers, yeah.
The markers. The minimum is 3 because that's what you need to define a plane, right? I mean, with 2, you cannot define a plane. You can only define a line. With 3, you can already define a plane and the normal vector to it, and then you can perform the transformation to the unified coordinate system. So minimum 3.
Okay, great.
And it's also important, I've been testing this a lot lately, it's also important how you place them, right? I mean, they cannot be on the same flat plane. They need to be distant from each other with respect to the Q2 as well. If you put them too close together, the reconstruction is not so reliable. It's more prone to error.
Okay, nice. And maybe one final question. So when did you say
Yes,
this will be released? This will be released, the software or this capability?
The very shortly. I'm still testing things. Of course, you can test things forever and make improvements forever, but I'm going to the States in July for doing a live demo on this. So yeah, by next month, there will be a usable beta version, and naturally you will be one of the first ones to have it.
Okay, great. Thank you very much.
Yeah, we told you we were this was going to happen, and now this has happened, and of course, I mean, the day that this is usable and released for customers, you will know.
Great, thank you very much. I appreciate it. Yeah, like that's very exciting. Thank you.
Yes, it is. Thanks a lot, Othman, and we'll talk soon.
Yes, thank you.
Anybody else? Well, if not, it's almost 7 p.m. here in Europe. I say it's time to go out and enjoy the summer here. Thanks a lot for coming to this presentation. You know that we're always happy to talk to you, answer your questions, have discussions. You know where to find us. And until next time.
Thank you. Have a good one.
Thanks, you too. Bye-bye.
Goodbye.
Thank you.
Goodbye.
Bye.